Welcome back, everyone, to the fourth part of the section on Weyl quantization and the Egorov theorem. The next part is about the Wigner transform, which is important because in many works, people prefer to express the semiclassical limit as a semiclassical limit of states rather than a semiclassical limit of observables. So let me briefly motivate the definition of the Wigner transform. So quantum mechanically, there is the notion of expectation value. So to emphasize this, I call this the quantum expectation value. And this is defined for, let's say, a self-adjoint operator F and a wave function psi from the domain of F, which is, of course, in L2 over Rd. And because it's supposed to be a quantum state, psi has to be normalized. And then we define, and I'm using the this expectation value from probability theory to emphasize that I'm talking about the quantum mechanical expectation value. I'm adding a QM here. And this is just defined as the scalar product of psi with F psi. And because our operator is self-adjoint by assumption, this here is real valued. There also exists a classical analog. So that's the classical expectation value. So here I'm starting with a classical state, which means I'm given a probability measure mu on phase space. Probability measure just means that mu of R2D is equal to 1. And I'm picking a state F which is integrable with respect to the probability measure. And then I define the classical expectation value. Simply as the integral over phase space with respect to the measure mu. And now one way to introduce the Wigner transform is as follows. So when my operator, capital F, is the Weyl quantization of a small f, and of course I'm assuming that all the technical conditions are satisfied. Does there exist a measure and here to satisfy people who want to be more careful, I have to replace measure, I have to weaken it, and I have to introduce a sign measure. meaning that volumes, phase space volumes could be negative in parts. And I call this measure mu psi. Oh, let me write it in a slightly different fashion. So let me write d mu psi evaluated at x, which is just the Wigner transform of psi at x dx. So this here, you could read it as the definition. And the defining property is that the quantum expectation value of the Weyl quantized observable agrees with the classical expectation value with respect to the measure mu psi of the function f. And fortunately for us, the answer is yes. And we call the resulting measure the Wigner measure. And the answer is the Wigner measure. So usually the qualifier signed measure or so is omitted, even though the Wigner measure need not be non-negative. So let me give a quick derivation. For the purpose of the derivation, you can just pretend I'm working with Schwarz functions all around. And then we can extend these formulas by duality, which is quite evident that it's possible because, again, it's just a variable transformation coupled to a partial Fourier transform. So let's start with the quantum mechanical expectation value. And we're just using the initial definition of Weyl quantization. So we're having the symplectic Fourier transform of f. And now, because we're having the expectation value, we have to take the expectation value of the Weyl system at x. And now if we compare this with the equation that we want to end up with, we see that all we have to do is get rid of the symplectic Fourier transform, which we can do because f sigma, so this is like a scalar product of two functions. all we need is complex conjugation. So to push this to the other argument, well, we have to evaluate the symplectic Fourier transform not at x, but at minus x. This simply because we're lacking complex conjugation here. So as a reminder, this here is the classical expectation value with respect to what we call mu psi. And this implies that the Wigner transform of psi evaluated at x is equal to it's 1 over 2 pi to the power d let me write it out first, times the symplectic Fourier transform of the function. So I'm considering the argument of the Weyl system as the variable in which I take the symplectic Fourier transform, and because I'm missing complex conjugation here or here, I need to evaluate the symplectic Fourier transform at minus x. And now all we need to do is write this out, do a quick computation. So let me write this out. And let me also write out the second integral. Let me call the integration variable z, which comes from the scalar product. And then I have a psi of z complex conjugate times w of y, the Weyl system for capital Y, evaluated to psi, applied to psi, evaluated at z. And this here was equal to e to the minus I epsilon eta dot z plus y over 2 times psi evaluated at z plus y. And similarly, we can write out the phase factor here. So this is e to the plus I times x dot eta minus psi dot y. So now what we would like to do is we would like to factor out the eta here. So let's do that. So this is equal to e to the plus I eta. And then I have an x minus epsilon times z plus y over 2. And the remaining factor is e to the minus I psi dot y. We will leave the second factor alone. But here we see that apart from this phase factor, everything else is independent of eta. So we can take the integral in eta. So let me do this here, which gives me a delta. So I have the prefactor from before. Now I have only an integral over small y and small z, which are just the spatial components of phase space. Then I have the remaining phase factor. Then I have 2 pi to the power d times a delta of x minus epsilon z minus epsilon y over 2 times psi of z complex conjugate psi of z plus y. Now, if I apply this delta function, because I would like to integrate over z, I have to take care of this prefactor epsilon. And once we integrate, so here we integrate now over z. So I'm getting 1 over 2 pi to the power d times epsilon to the power minus d. This just comes from one of the rules of how to work with delta functions that have been scaled. And now we have the integral in z. The integral in y, of course. The z integral has just been killed off by the delta function. And now once we do the substitution, what we get is epsilon x divided by epsilon minus y over 2 complex conjugate. And then for the other one, since we're adding y, so I get minus y half plus y, so plus y half. So this is x divided by epsilon plus y half. And this is the final form up to equivalence. So you could still, for example, you can replace y by minus y, then these signs flip, and also this sign flips. In the literature, you will very often see, so this is in the microscopic spatial scaling. If you replace microscopic by macroscopic units, the epsilon goes here, and so forth. There are also some, there's some variation with respect to this prefactor, but the essential structure is the same. You can quickly convince yourself that because this is a partial Fourier transform and a linear change of coordinates, if psi is a Schwartz function, then the end result will be a Schwartz function. So this I will just give as a statement without proof. So the Wigner transform maps Schwartz functions, so here wave functions, so they are Schwartz functions on RD to Schwartz functions on phase space. Let's list some properties. So the first one is that the Wigner transform of a Schwartz function is real valued. The second point is that W psi need not be non-negative. So that is what I meant when I wrote that Wigner measures are signed measures. in a sense, the negative parts of the Wigner measure are a feature, a remnant of quantum mechanics. They are due to interference effects from quantum mechanics. So there exists simple example, something like x times e to the minus x squared. That its Wigner transform is has regions where it's negative. And then you have relations for the marginals. What are marginals? Well, if you integrate over the spatial component, for example, what you get is nothing but the Fourier transform of the wave function evaluated at psi in absolute value squared. And similarly, when you integrate over psi, what you get is epsilon to the minus d of psi of x divided by epsilon in absolute value squared. And that implies that if you integrate the Wigner measure over phase space, then this just reproduces the L2 norm squared of your wave function. So if the wave function is normalized, then this will be 1, which is one way of saying that the Wigner measure for normalized wave functions, which in quantum mechanics, this is the assumption to make, you get a pseudo probability measure. Pseudo because you're dealing with a signed measure. So in the last step, and I will be brief here, it's also clear how to extend it to operators, to more general quantum states and to operators. And both are important conceptually. So in quantum mechanics, generalization of the state where you view a state as a normalized wave function up to a global phase is the notion of density operator. Which is a self-adjoint operator that is non-negative and has trace 1. And then let me also introduce the operator kernel. So assume I'm given a bounded operator T, then the operator kernel is the tempered distribution that satisfies the following. So we know that every bounded operator has a distributional operator kernel. This is so-called This is the content of the Schwarz kernel theorem. And what is the operator kernel? Well, if I apply the operator to a wave function psi, to an L2 function, then I can view it, at least formally speaking, as an integral over y of kt that depends now on x and y times psi of y. So, for example, the identity operator has the delta function as its kernel. And then you can define a Wigner transform for operators, applied to operator kernels. And what you do is you basically take the formula from before and you simply replace the psi and psi bar by the operator kernel, and you just have to be careful which of the arguments that you're going to choose. So this argument goes to the right. So this is the second argument, this is the first argument. And of course, initially you can define this for for operators whose kernels are Schwarz functions, but then you again see there's a linear invertible coordinate transformation and a Fourier transform. So this extends nicely also to tempered distributions. So that's why, let me just write on S RD times RD or S prime RD times RD. And what is the relation to the initial definition? Well, if you choose as your operator the rank 1 projection psi psi, then the operator kernel is not surprisingly psi of y complex conjugate psi of x. So this you can check just by direct computation. And hence, the Wigner transform applied to the operator kernel of the rank 1 projection agrees with the Wigner transform of psi from before. And you can check if psi is normalized, then this defines a density operator. So the normalization, in fact, gives us the last condition. The first two are always correct. And that's already it, right? So now let me just summarize the relationship between the Wigner transform and the inverse of Weyl quantization and the expectation value for more general states. So let rho be a density operator. And for simplicity, let me just assume that its kernel is in fact a Schwarz function, not just a tempered distribution. So because the density operators are trace class, they are all bounded. So they at least have a distributional operator kernel, but let me just assume for simplicity that this one has a Schwarz class distribution kernel. And f is also assumed to be a Schwarz function. Again, the statement below extends but I'm just doing this to avoid having to deal with technical complications. So then the expectation value with respect to this, the quantum expectation value with respect to rho, is just the trace of op f applied to rho. And this is equal to the classical expectation value of the Wigner transform with respect to the kernel of rho and f. For this special case where rho is a rank 1 projection, the old quantum mechanical expectation value with respect to the function, the wave function psi, is nothing but the above generalization for the rank 1 projection. And the second point, which conceptually is also important, is that the Weyl quantization has an inverse, and it is given by the Wigner transform applied to the operator kernel that I'm dequantizing. This is quite handy. So we have a dequantization rule. All right, that's all I wanted to say about the Wigner transform. Next up, we're going to introduce magnetic fields.